Hello everyone and welcome back to Winter Data Meetup. I hope you all enjoyed the insightful talks and discussions we had so far. Meet Ali Oztas, senior data scientist with expertise in deploying open source language models. Join him and he explores the effective utilization of LLMs across various environments, from GPU instances to local machines. Don't miss this opportunity to learn about creating intuitive REST APIs and conducting comparative analysis of different frameworks, and this insightful. Uh, Now, before we dive into our session, I'd like to take a moment to ask you for your support in helping us grow our community and recognize the speakers. Firstly, if you enjoyed the content we are providing and want to stay updated on future events and talks, please consider hitting the like and subscribe buttons below this video. Now, for something a bit special, in the video description below you will find the link to the talk page, where you can provide your feedback for this talk, give speaker a badge, and rate the session if you like or if you don't like it. Through the session, if you have any questions or insights you'd like to ask and to share with us, don't hesitate to type them into the chat box on YouTube or via community platform. Our team will be monitoring the chat box closely and will collect all the questions to discuss with Ali after the presentation. And now, ladies and gentlemen, let's welcome our speaker to share his valuable insights with us. Ali, floor is yours.
Okay, hello everyone. I'm Oztas. I'll be presenting today to talk about the cracking the code, a deep dive into open source language model deployment and inference. So about me, I'm a senior data scientist at EPAM Systems with 5.5 years of experience in machine learning. I had prior experience in time series analysis and tabular data, but I'm mostly focusing on NLP with the rest of my career. I'm currently working in the generative AI research lab of EPAM, where we're trying to employ and research the newest technologies in our projects. So my contents are going to include when did we start accelerating our work about this? Why are we accelerating open source and not only relying on closed source services? Introduction to the respective components. I will be talking about quantization, how we can serve our models. I will be briefly discussing what is the future work and what does future hold for us for now. And question answering session will be also done as well. So first, I would like to start. So previously, we also had encoder, decoder, transformer models such as Flunk T5. We had GPT-2 and we had GPT-3. But for the open source development, LLaMa 2 release on July 18th, 2023 is the main catalyzer here. The reasons being it has commercial license that's only restricting Google level companies which have 100 millions of users. It has three possible sizes, 7 billion, 13 billion, 70 billion, which enables us to use different hardware and to test different setups. So why are we using open source to begin with? The main sections are, so the consistency is a big issue here because the closed source models, they are being developed constantly, they are being censored, or of course, censorship is a problem, should be considered, but the consistency is also another worry because let's say if the model is good at coding and the next day it is not, you won't be able to perform your task in a consistent level. And API downtimes are another issue because you want to be able to access your model at any time. So if you use your own premises, you will be able to control that. And let's say you want to release a new release algorithm, new release service on the closed source premises, and rate limits are a big issue there because they mostly limit how often you send requests, and also there are no random board problems in your premises as well. So for privacy, most of the companies they want to keep their data private because they don't want to leak personal information. They don't want to do anything else. So this is a big issue in this area, and also licensing. The open source models are MIT license, Apache 2.0 license, which we can utilize however we want with minimal restriction. So also performance. Let's say closed source services, because they have more of the budget, Of course, initially they perform better, but open source community and new papers are released every day, and the community is employing these papers on research. For example, just last week, a new SQL coding model has been released, and it's outperforming GPT-4 right now. And also, if we have a specific domain in our task, or let's say if we have a specific task and with the respective data, we can fine-tune our models employing technologies such as direct policy optimization, supervised fine-tuning, LoRa adapters. So these are different fine-tuning methods which enable your model to perform better in the respective domain. Also, finally, the cost is also another important issue here, where, let's say, given a single GPU instance, we can host multiple models, which can enable us to use multiple models in a lesser cost. We can utilize new frameworks that are being updated constantly. Also, quantization is another thing that I will be touching on. We can reduce the memory requirements of the model and utilize it with lesser memory. And also, we can just use our models locally and just perform whatever we want. But one of the issues here, there are so many components in open source model deployments, and there is batching, there's hardware, there's quantization, there's attention mechanism, tons of frameworks. So this talk is also going to include how we can separate them from one another and decide accordingly. First, I will be talking about the hardware and why do we prefer GPUs mostly. One of the main reasons is parallelization because they have many more cores. They are much more parallelizable than CPUs, where in GPUs we perform mostly matrix multiplications or matrix operations and transformations. So this is enabled in GPUs. They have better memory bandwidth. They have better caching and memory hierarchy. Their architecture is more supported for these respective tasks. And also initially, let's say for NVIDIA as well, different precision types and quantization support is more enabled on GPUs rather than CPUs, which I'll be talking about them further as well. So as mentioned, I just want to touch about what is floating point precision, because I'll be touching about them in quantization as well. It is the way that we represent the real numbers with a wide range in computing. And every number has a sign, a mantissa, and an exponent. And mostly 64 and 32-bit quantization is used. But if you want to delve deeper, we can reduce the memory usage with float 16 and quantization. So as mentioned, we are using floating point 32 bits, which has a total of 32 bytes, 23 mantissa, 8 exponents, and a single sign. The details here are not so important. What's the most important part is we can see in the graph that if we reduce from float 64 to float 32, we don't lose that much performance, but we can utilize half the memory, which is a massive gain right now. If we reduce that from float 16, you lose most of the performance. It drops from 90% to 50%. So float 16 mix and also brain floating point 16, which is one of the newly released floating point systems that it enables your model to run on float 16, and it also has better bit separation. So it is more optimized for these tasks. And we can see that we even have better performance or close performance to float 64 with quarter of the memory. But we can go even further and quantize our weights not only to float point 16, so reduce the precision type not only to floating point 16, but we can also reduce it to int 8 or int 4, or there's even work for 3 bits or 2-bit quantization. What quantization is, it allows us to represent our original model weights in other precision types. What it allows is it reduces our GPU utilization, so we can go for cheaper options. It reduces latency, which is we can answer better in a quicker fashion to the requests, and it increases throughput, which means we can answer more requests given a time frame. So first of all, for int 8 quantization, it is the representation of 16 float vectors, so integer 8 data type. The process here, if you're interested, I'm leaving in each of the slides, you will find respective links. So in each of the types, you will find respective links. So I can share them as well. And NVIDIA has an implementation in faster transformer library that we can say that in larger batch sizes, it can enable 5 times speed up compared to floating point 16 precision. We can go even further, and we can use Infer quantization, which is mostly being experimented on right now, and we will be mostly focusing on this, on quantization types. It is a representation of floating point 16 vectors in Infer data types. And again, it is a further improve the latency and increase throughput, and also reduce the memory usage further, while keeping the performance as best as possible. And again, it's most experimental, and newer GPU models mostly support this. And again, I'm mentioning hardware and GPU utilization a lot. I'll be just talking about how much memory does these models consume in different integer or floating point precision types. Let's say 7 billion model is a reference, and in 32 floating point, it does require 28 gigabytes of RAM. But if we reduce that, the usage is sort of linearly. In Int4, we can see that it is dropped to 3.5, which is 8 times lower than that. So we can use 8 times lesser memory, which can enable us to use cheaper hardware, and again, keeping the best performance available. So for quantization, especially Infer quantization, which is being discovered a lot, there are different algorithms and different trade-offs, and I'll be talking about them. And we can just initially talk about the libraries of bits and bytes algorithms, bits and bytes, GPTQ algorithm, and there's EPAM kernel editions, and also activation awareness quantization, AWQ. So first of all, bits and bytes. It can be, you can just use whatever model you want, and it's heavily integrated in the Hugging Face ecosystem. And we can just pass the parameter that is load in 4-bit equals true, and the model is being quantized on the run. It takes a bit of time to quantize, but it reduces the memory from floating point 16 to int4, which is 4 times lesser memory, and again keeping the latency and throughput and the performance as best as possible. But there are also further enhancements on this one. One of them being GPTQ and EXllama kernels. GPTQ introduces an optimization process after the quantization is done, which improves the perplexity. Perplexity is a metric that is mostly used in large language modeling to metric the performance of the model. And EXllama provides additional kernels. By kernels, I mean these models do run in GPUs, and GPUs mostly in NVIDIA and CUDA. So these CUDA kernels does allow better matrix transformations and better performance. So EXllama does provide that. Moreover, there's activation awareness quantization. We don't quantize all the weights. We quantize some of them utilizing the activation awareness, which improves latency and also, and again, keeping the perplexity and performance of the model as close as to the floating point 16. So just to compare how do these quantization mechanisms reflect with each other, we can see that in throughput, we want throughput to be high, so because we want to process as many requests as possible given a time frame. So we can say AWQ quantization is the closest one in throughput to the unquantized version, and GPTQ and bits and bytes does change. And also for the latency, with the increasing batch size, latency is how much time does a single request take. And we can see that for different quantization types, latency and throughput should be checked because they do give separate results. And with respect to your trade-offs, you should decide in between them. So there's also as I mentioned, memory usage is an important area, and also the perplexity here. One other important metric is tokens per second. I'll just be discussing that. We can see in the left graph how much memory does the respective model consume, because it doesn't just stop at AWQ or GPTQ or XLaMa kernels. There are further parameters in each of these sections. And we can see that the memory usage of a 13 billion model in 4-bit quantized can range in between 10.5 gigabytes to 8.5 gigabytes, 8 to 8.5 gigabytes. And we can see that in the right section, for tokens per second, for each of these, the performance changes as well. So we can see that XLaMa kernels mostly provide the best result, and we can see that the best perplexity model, which is half of here, is performing one of the best tokens per second solutions as well. Moreover, I'll be discussing the serving frameworks, and while discussing that, so let's say we have our models, we quantize them, and we want to utilize them. And so how can we do that? I'll be using the term parallelism, batching, and throughput latency a lot that I'll be explaining. So the parallelization is distributing model in a way that we can utilize multiple GPUs. There's data parallelization. Data parallelization means that we just create the same instance of the model in separate GPUs. In training, which is not the topic of this talk, the data is distributed as well. But in inference, which is the topic of our talk, the incoming request is routed into a GPU. So if we have multiple requests, we can just direct them into separate GPUs and utilize our infrastructure. Moreover, in model parallelization, there's pipeline parallelism and tensor parallelism. Pipeline parallelism does mean that we just sequentially distribute the layers, which is not the most efficient solution. Therefore, the tensor parallelism has been created. Layers are distributed in a way so we can parallelize our requests much better. And there's also batching. Batching does mean how do we handle our requests? Generally, there are 3 types of batching in inference. Static batching, client just forms a batch. Dynamic batching, the batches are being created on the fly. And also continuous batching, which is state of the art. And I'll be explaining this further in the framework section. And of course, while talking about this, what are our trade-offs? How do we decide between each of the frameworks that I'm mentioning? While you're if you want to research about this, how can you decide as well? So one of the 3 aspects is performance. How does it utilize hardware? Does it allow quantization? What does it allow? And also the user friendliness, which I'll be talking about. And also, how can we utilize them? We can utilize this in our local machines using our terminals or using respective user interfaces. We can just deploy them on our phones or edge devices, or we can just serve them in cloud and use APIs. One of the serving frameworks is OpenLLM. It's an open source. It does allow to deploy your model either on cloud or on premises, and it does allow you to utilize your terminal as well. It does allow utilization of multi-GPU and different quantization methods. If you want to start testing different models, OpenLLM is a perfect way to start because it's user-friendly and also it doesn't require you to do much manual work. But if you want to further improve your local usage, LLaMa CPP is also another great way to utilize. It is supported in macOS, Windows, Linux. You can utilize the newest models, LLaMa, Phi, mixed RAM models. You can even use image and text models such as Lava. And it is also supported by user interfaces such as LLaMa, Text Generation Web UI, which is perfect. And it also does allow quantization as well. It has a separate method called GGUF. So you can just use whatever model you want if your hardware allows it. But if you want to use multiple models in a serving infrastructure, how can you do that? For example, there's this chatbot arena. It does implement a mechanism that is sort of similar to chess. Users rank their language models given a prompt. And so you want to host multiple models. So Fast Chat does allow you to do this. It does have a single controller, and it allows you to use different models and different workers, and it allows you to utilize different backends as well. And it's being used in Chatbot Arena right now, which is serves over 6 million of requests for multiple large language models. One of the other frameworks is C-Translate 2, and it does allow you to utilize int8 quantization as well. It's also parallelizable in multi-CPU and GPU. It does allow you to asynchronous execution, but utilizing C-Translate 2 is a bit bothersome because it does require you to convert your model into their format. It does take a bit of time, but if you want to use data parallelism and just test out quickly what it can do, it is a fast solution as well. Let's say if you want to use edge devices, which is one of the issues most of the libraries do not cover. MLC LLM is a universal solution. It again does allow you to convert your model into their preferred format, so not the most user-friendly, but given a trade-off that you can utilize web browsers, you can utilize your local machines, you can utilize edge devices. It does take the trade-off that if you make a bit of effort here, it is worth the effort, so you can employ your model however you want, and it does also provide one of the fastest solutions. So I'll be talking about one of the newest released ones. One of them is VLLM, and it's one of the most open source and state-of-the-art inference backends, and it does allow techniques such as page attention, which is a novel technique released by them, and also continuous batching, as mentioned before, which can visualize here. In the left side, we can see the 10th GPU memory and how it's used given a request. So we can say in the left side, the half of it is empty. So we are just waiting for the first serving and first request to be handled, so we can just send more requests. But in the second section, in the right side, we can see that we can use the empty spaces as well. If we allow our memory usage in a good fashion, we can employ the empty memory and just be as efficient as possible. Moreover, there is also, besides from continuous batching and also how we can split this memory, as I mentioned in here, DSP FastGen does create a new novel method called dynamic split fuse, where we can see the left side that the separation of these chunks is not the most optimal in other serving mechanisms. But DeepSpeed library does take care of that to improve latency and throughput. In the right graph, we can see that for the Mixtral model, it does increase latency and throughput given different hardware usages and different generations. And one of the final two libraries, one of them is TensorRT LLM. You might have seen about this, which is released by NVIDIA. It does allow you to use NVIDIA's services and build TensorRT engines, which does contain their own optimizations, so they are a bit more optimized. And we can see that it does support multiple quantization methods such as squeeze LLM, AWQ, and GPTQ. And we can see that there's only a minimal amount of memory loss, 1% or 2%, or even 0.1%. In the right side, you can see that if you want to utilize which quantization type, for example, there are different trade-offs, performance improvements, how does it impact our accuracy, and also user-friendliness and how much time does it take. So if we have the hardware, the floating point 8 is one of the best options to use. Further, we can follow that with int8 and AWQ and GPTQ. And the final release, serving framework for large language models is SGLang. It has been released recently. It's using a attention mechanism called Redis attention that does try to serve your request in a way that it can be partialized, and for the same part, it tries to caches them. So we can see on the left graph that it is comparable or better than the VLLM library in the respective sections, especially for multitasking. But also we can say this is one of the first frameworks that does allow us to utilize LLaMa multimodal deployment as well. And we can see that it does perform much better than Hugging Face inference as well. So the main notes that I'll be stretching here will be, if you want to utilize these models, for backend, we can select from VLLM, DeepSpeed MAI, TensorRT LLM, or SGLang. The preference of this is mainly from whatever you prefer, and please experiment with your project, because for different domains, as a note, these are being developed on a daily basis. So today's presentation has been performed lately, but let's say if you want to do this a month later, they can develop a new algorithm and employ that. And again, TensorFlow VLLM SGLang does support quantization, so we can go, let's say, 3 times cheaper or higher. For the metrics, I'll be talking about the latency, throughput, how much time does it take for the first token, and for the output token, how much time does it take. So we can see that in one of the important aspects, in the left side, we can see the multiple GPU utilization is also the communication between GPUs, which is another important topic. And also in the right side, we can see that it does impact throughput and latency as well. So we should experiment for our hardware utilization as well, because it does give a separate result. So we want to optimize latency and throughput given our hardware. Also for performance for tokens per second, in the left side, we can see that there are, for different inference frameworks, different tokens per second is received. And we can see that currently TensorRT LLM for a 7 billion model using 2 L4 GPUs did give the best optimization for batch size 1. But also in the right side, we can see that for changing batch sizes, how we can handle our requests, let's say in this DSP if it is only 1, if we have 35 tokens per second in batch size 1, if we increase that further, we can go up to 240 tokens per second. So it increased linearly. But in different frameworks, it may not be linear. So this is also another important thing to discuss. How does your inference framework handle your requests, given separate batch sizes? So finally, what is the future work here? Because there is tons of developments here that you might see on a daily basis. So, and most of these serving frameworks do try to create their own and also implement the existing solutions as well. As mentioned in the NVIDIA's and TensorRT LLM section, floating point 8 is coming. Is starting to being released in the newer GPU models, and it's being supported by Microsoft MS-AMP library and also NVIDIA's ALMA toolkit. There are new decoding algorithms. By decoding, I mean the generation of generation of text, so it can be faster. There is Medusa, speculative decoding. There is a REST algorithm, and there is look-ahead decoding. Each of these do try to improve your performance of generation with different methods. We can also utilize longer context. Let's say most of these models, the maximum context length, we can use 32,000. But for example, GPT-4 has released 128K. So how can we go further? There is Yarn and long LoRa papers algorithms, which are also being employed, which can increase your token usage to 100,000, 200,000 with minimal performance decrease. And finally, and again, we should employ and experiment on the latest inference frameworks such as LLM, DeepSpeed-MAI, TensorRT LLM, and SGLang. So thank you for listening, and now we can start the questions.
Yeah, thank you very much, Ali. Very interesting presentation, detailed. Yeah, so we have several questions. Let's move to them. Yeah, first question: is it possible to run LLM on Raspberry Pi?
Yes, in MLC LLM, I just saw a paper. I just saw an article that recently that MLC LLM also does allow you to convert your model in a way that in that way. Please, if you can contact me, I can try to send you the respective article as well.
Yeah, because looks like depending on your hardware, you need to choose a proper library.
Yes.
Right. So not everything can be executed like on any hardware.
Yes.
You need to choose. And yeah, you also mentioned that performance of GPU is much better than CPU. Maybe you have some. Maybe you have some numbers. Yeah. So.
For the numbers, so one of the experiments that I have done it does change with respect to the GPU, but it can be from 8 times, 10 times, or further faster. So in one of the articles is being mentioned, let's say LLaMa CPP is mostly CPU optimized, and it also enables GPU, but also it can be 3 times faster for that library as well. So for different frameworks, the CPU and GPU trade-off does change, but generally it is 3 times, 5 times, or faster than that.
And yeah, why performance is different on different frameworks? Is it because of this uh,
As not
quantization?
only, sorry to interrupt, not only the
Yeah.
quantization part, but I mentioned that, for example, SGLang does employ a mechanism called radix attention, or VLLM does utilize page attention. So not only also they each of them have their own CUDA optimizations. So we do perform these transformations, matrix transformations on GPU, which is using CUDA in the backend, and each of these libraries have their own CUDA scripts. So not only the quantization, but also how they handle the given model, and also for the quantization, how they handle quantization is separate as well. So
Uh-huh.
each of them have their own implementations.
Yeah, and does it, so regarding quantization, does it mean that we can it helps to use like LLM on cheaper hardware? So you describe this using of int 4, int 8,
Yes.
so that we can use cheaper hardware. Uh, yeah.
Yes. For example, we can go even further than int4 if you don't want, if you are okay with the some performance loss. Lately, a library called AQLM has been released that you can reduce your weights to int2 with minimal amount of performance loss. And also it's, let's say with 32, compared to 32-bit, it's average of like 16 times cheaper. Also 16
And
times less hardware required.
uh-huh. And can it affect the results? I mean, the results
Yes.
of a model, not only performance, I mean, but for example, I don't know, the
Latency,
yeah.
it does improve, it does change how much time does a request take. It does change how many tokens are generated given a second. As mentioned in the NVIDIA TensorRT LLM section, and also in the graphs, different libraries also handle it differently. But again, it does improve your throughput, impact your throughput latency or tokens generated per second.
Uh-huh. Yeah, we also have a question regarding LLaMa. Is it a production ready framework or it's only for home projects?
For LLaMa language models, are
Yeah.
yes, it is. LLaMa 2 is production ready. So production ready means that what it's also with respect to what is your project. Let's say if you have a coding project which you want to automate every section of the model, LLaMa 2 is not a coding model. There is code LLaMa or DeepSeek coder models. So, but for general purpose usages, let's say LLaMa 2 is mostly production ready. But again, what is your project is also another important question here.
Uh-huh. Okay. Yeah, and maybe last question. Could you advise some material to learn more about LLM and all the specifics of hardware utilization?
Of course, I
Maybe
can
some
share.
forms. Yeah.
I'll be sharing some links if I can. Other than that, I can mention Coursera is releasing courses in lately a lot, utilizing different libraries as well. So you can utilize Coursera for this, which is deep learning. Sorry, Coursera deep learning AI. Deep learning AI is releasing courses in Coursera, which is highly performant, and they are mostly informative. And they do allow you to learn about different trade-offs between serving or in respective domains or models as well.
Okay. Yeah. Thank you for your answers. Looks like we don't have any more questions. And I think that concludes our session. So thank you all so much for joining us today. We hope you found this session insightful and inspiring. In this video description below, you will find the link to the talk page where you can provide your feedback to this talk, give speaker a badge, and rate the session. Also, if you have any questions, you can type them on this talk page, and Ali will reply them offline
Yes,
after the session.
yes.
Additionally, if you'd like to revisit the session, you can download the presentation file and watch the recording on the talk page. Please check video description for the link. So thank you very much, Ali, for coming. We could not do it without you.
Thank you for your time, and thank you for
Thank you very
listening.
much. Yeah. Bye. Have a good day.
Bye bye. Have a great day.